Hey, what's up everybody, and welcome back to Quantum Mechanics for the Working Professional. Today we're going to be doing another problem solving session. Specifically, we're going to look at problem 3.4. And our aim here is to essentially gather the spin up and spin down states for a specific, although somewhat generic, spin operator. That is to say, a mixture of spin X and spin Y. You could reframe this problem as just an eigenvalue problem. That is to say, a typical problem in linear algebra. And the one thing about learning linear algebra is you cannot do enough solving of eigenvalue problems when you're first getting started. So if you've done this already before, great, let's do another one. So without further ado, let's get started. So we are interested in a specific orientation of our Stern-Gerlach device, right? So we're interested in the spin operator S, which you remember has components Sx, x hat, plus Sy, y hat, plus Sz, z hat. And we're going to be looking at a specific angle. And we've already kind of worked through a problem like this before. So we're going to be looking through a specific angle. We'll call it, I don't know, r, the r direction, which will be cosine theta in the x hat plus sine theta in the y hat direction. So if you like, you can imagine putting a Stern-Gerlach device in the ground with a magnet orientated to measure spin in the x direction, like right in some direction, like say this way. And then we're just going to rotate by some angle in the y direction by an angle theta. Great. Okay, so first, before we figure out what the up and down states should be, let's figure out what the operator precisely is. So S dot R, which is our unit vector in this theta direction, was given by Sx cosine theta plus Sy sine theta. And you might recall that Sx and Sy are both h bar over 2 times one of the two Pauli matrices. So for this case, this is h bar over 2 times 0, 1, 1, 0 cosine theta plus h bar over 2, 0 minus I 0 sine theta. So, and of course, the sum of two linear operators is, in fact, a linear operator. That is to say, the sum of two matrices is a matrix. So let's just add everything together. This is h bar over 2 times 0 plus 0 cosine theta minus I sine theta, cosine theta plus I sine theta, and 0. And you might recall from our problem discussion of the Euler relation, and check that video out if you haven't yet seen it so far, when you see something like cosine plus I sine theta, you should be thinking e to the I theta, right? Because that's how you can represent them. So this matrix actually looks like h bar over 2, 0, e to the minus I theta, e to the I theta, 0. Super easy. Great. Okay, so now let's think about taking this operator S theta and acting on a quantum state psi. Okay, so to that end, let us have S theta acting on a generic quantum state psi, which has generic components, say alpha and beta. So this is h bar over 2, 0, e to the minus I theta, e to the I theta, 0 times alpha beta. And our goal here is to figure out the values of alpha and beta so that we find what spin up state looks like in this peculiar theta direction. Good. So we can begin by exploring how this operator acts on this state. Multiplying out, we see that's e to the minus I theta times beta, e to the I theta, I theta times alpha. Great. Okay, so that's S theta acting on psi. Now, what we want for an eigenvalue problem is to have something of the form S theta psi. Let's call it Let's call it up in the theta direction is equal to h bar over 2 times the same vector back. And similarly, for the down eigenvector, the down state, if you like, the down quantum state in the theta direction, we want something that looks like, S acting on that state is minus h bar over 2 down in the theta direction. So our task is to find alpha and beta for both of these two states. And to do that, essentially we solve linear equation, hence the name linear algebra. I'll show you what I mean. So let's start with the spin up direction. So let's define the variables for our spin up state. Let's call that, theta up. Let's call it, I don't know. How about A and B? Great. Okay, A and B. So now we want to know S theta acting on theta up needs to equal h bar over 2 theta up. Okay, great. So that's 0 e to the minus I theta, e to the I theta, 0. AB needs to equal, oh, there's an h bar over 2 here, h bar over 2 AB. Good. So the first thing we observe is, well, h bar over 2, duh, that part comes out, so that's easy. And we have two equations here and two unknowns. So let's first evaluate this matrix vector product. So that's e to the I theta b, e to the I theta a. There's a minus sign there, and that's equal to a and b. Okay, good. So what does that tell us? That tells us that a is equal to e to the I theta b, and b is equal to e to the plus I theta a. So one thing we can tell right away is that these two things are consistent. So one of the tricks to solving eigenvalue problems is you kind of need to guess a value for A or B. And one of those guesses is typically the number 1, although sometimes a good reasonable guess is also 0. But in this case, let's just guess the number 1. And so if we let, say, A equal 1, then B must be e to the I theta by this equation here. And if that is in fact the case, we see that B, it's e to the I theta, that would cancel those two, which would make A equal to 1, which is what we started with for our hypothesis. So great. And actually what we've just shown is that this is consistent. And when you're at that level of consistency, blah, 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 you're done. Right? Does that make sense? I don't know, but we'll do it again for the spin down case. So what I'm trying to say is that the state of spin up in the magnet's theta direction is given by the vector 1 e to the I theta, sort of. So this would definitely solve the so-called eigenvalue problem. So in other words, S theta acting on this state is going to give you back h bar over 2 times that state. But we need to normalize the state. That's just kind of another step that we've demanded of ourselves. And so to that end, we just need to compute the bracket up with up. So this is, remember, 1 e to the minus I theta, remember, because we take complex conjugates for the bra vectors, multiplying by 1 e to the I theta, which is just 2. Hopefully that's quick now. So once again, we need to divide by the normalization factor, 1 over the square root of 2. So actually, what we have, to normalize this state, we demand that theta up go to 1 over the square root of 2 times 1 e to the I theta. Awesome. Okay, so that is our eigenvector for the eigenvalue of h bar over 2. Now, what do you suppose the eigenvector, the spin down quantum state, is associated to this particular operator S theta? I'll give you a hint. There's probably a minus sign somewhere convenient, but let's double check just to make sure. So we're going to solve this problem one more time, and hopefully I'll be a little bit clearer about answering it. So S theta on the down theta state should be given by the spin down eigenvalue, that is to say minus h bar over 2 times the down theta state. Right? So let's call the down theta state, I don't know, C and D. Why not? So we have 0 e to the minus I theta, e to the I theta 0. C and D needs to equal minus h bar over 2 times C and D. Good. So let's multiply through and solve, right, these linear sets of equations. So this is once again D e to the minus I theta, C e to the I theta is equal to, there was an h bar over 2 here, right, because it's a spin operator, of course, minus h bar over 2, C and D. So those h bar over 2's cancel, as they should, and we're left with the observation that, once again, d e to the minus I theta is equal to c minus c, excuse me, and c e to the minus I theta is equal to minus d. This is very similar problem. There's just a minus sign included around. So you might ascertain that there is a very similar solution to this very similar problem. That is to say, let c equal to 1 as per usual. And so that would imply that d is equal to what? Minus e. Oh, I screwed something up here. That's a positive. Yeah, minus e to the I theta. Big surprise. I know. So does this in fact check out? Well, if d is equal to minus e to the plus I theta, then this would mean that c would be equal to 1. So yes, this checks out. So we have theta down is given by 1 minus e to the minus I theta. Oh, that's a plus I theta. Sorry, excuse me. Theta down is equal to 1 and minus e to the I theta. Once again, we have to normalize this particular state. And so we take theta down with theta down. This is given by 1 minus e to the minus I theta for the bra, 1 minus e to the plus I theta for the ket. So the bracket becomes 1 minus 1 plus minus e to the minus I theta times minus e to the plus I theta. In physics, there are so many minus signs. So we are left with 1 plus 1 equals 2. So once again, we divide by 1 over the square root of 2. And so we take our normalized quantum state representing spin down in the theta direction to be 1 over the square root of 2, 1 minus e to the I theta. Awesome. Okay, so this is the generic procedure for how you would solve an eigenvalue problem in 2 dimensions. You can do the same thing in 3 dimensions if you want to work with bigger matrices. If we have, say, a spin 1 state where you would have a 3-level system and so on and so forth. But obviously, it gets much harder the more dimensions you consider. So in summary, we have been looking for the quantum states associated to the operator S sub theta. Those quantum states, that is to say those eigenstates, those eigenvalues, eigenvectors, which are measurable quantities. What you can actually physically measure is the eigenvalue is the physical measurable, the item that you're measuring, and the eigenstate, the quantum state associated to each eigenvalue, the so-called eigenvector, gives you what the quantum state would actually be. So the quantum state associated with the operator S sub theta can either be found by measuring in the theta direction to be spin up theta, which we have found equal to 1 over square root 2, 1 e to the I theta, or down theta, which is equal to 1 over the square root 2, 1 minus e to the I theta. Those are our representation of a spin 1/2 system for a generic angle in the plane, say. Great. So that might have not been extremely clear, but hopefully it was a good example that you were able to work through on your own. I would strongly encourage you to do many of these problems, kind of invent your own problems if it really takes. Just find eigenvalues and eigenvectors for 2x2 matrices whenever you can. That's all for today. Hope you're having a great winter so far. We will see you in chapter 4, I believe, if there are not other problems yet to do. Have a great day, everybody.